India is initiating a $214 billion infrastructure expansion. The country aims to scale its nuclear energy capacity from 8.8 gigawatts today to 100 gigawatts by 2047. A gigawatt is 1 billion watts, roughly enough to power a medium-sized city. Current 8.8 gigawatts is dwarfed by the 91 gigawatts India plans to add, requiring $214 billion. The timeline below shows India took 60 years to build 8.8 gigawatts. Now it must deliver 10 times that in 22 years. Executing a 12-fold capacity increase on such a compressed schedule turns nuclear energy from a long-term research interest into an immediate industrial mobilization. The national grid is under increasing pressure. Renewable energy sources like solar and wind now provide nearly half of India's installed capacity, but sudden weather shifts can trigger cascading blackouts when the sun sets or the wind stops. This map shows the external pressure from the European Union. They implemented the Carbon Border Adjustment Mechanism, or CBAM, a tariff penalizing imported goods like steel based on carbon emissions. Without clean power, Indian exports become too expensive for global markets. Domestically, hyperscale AI data centers are pulling massive amounts of electricity from the grid. These facilities require constant 24/7 power to function, which intermittent renewables cannot provide. Furthermore, India imports 85% of its crude oil. This reliance on foreign fuel sources creates a strategic vulnerability for an expanding economy. This radar chart plots energy sources across 3 axes: carbon output, reliability, and land footprint. Nuclear energy reaches the required threshold on all 3 axes simultaneously, emitting only 12 grams of carbon per unit with 90% reliability. Nuclear energy provides the specific load profile required to keep the grid and economy functioning. Without it, the country's industrial growth hits a physical limit. If the technology is so vital, why has it remained stagnant for 6 decades? The Atomic Energy Act of 1962 created a total state monopoly, legally barring private capital from building or operating nuclear reactors. Later, the 2010 Civil Liability for Nuclear Damage Act allowed plant operators to sue equipment suppliers if an incident occurred. This placed catastrophic financial risk on global manufacturers, which effectively and immediately ended foreign participation in the entire sector. Intense domestic friction, like the 2012 protests at the Kudankulam plant shown here, further complicated new projects and caused years of construction delays. While India clearly possessed the engineering expertise, the sector was paralyzed by a restrictive legal and financial architecture. In late 2025, the Indian Parliament passed the Shanti Bill. This legislation dismantled the previous state monopoly, ending the government's exclusive control and allowing private entities to build and own reactors. The bill also shifted financial risk exclusively to the plant operator, removing the liability threat that had kept equipment suppliers out of the market for 15 years. Within days of the announcement, major industrial houses like Tata, Reliance, and JSW began allocating billions of dollars to develop their own captive nuclear power plants. By removing these 2 structural barriers, the government transitioned nuclear energy from a slow-moving research project into a commercially viable industrial sector. With $214 billion entering the space, a fundamental investor faces an immediate question: how do you actually buy into this cycle? The core participants in the boom, the reactor operators, uranium miners, and fuel fabricators, are completely off-limits to the public markets. This flowchart of the nuclear ecosystem shows the constraint. The primary nodes, mining, operations, and fuel, are strictly government-owned and unlisted. Retail and institutional capital cannot buy direct shares in them. Standard infrastructure investing fails here because the state controls the direct routes to capital appreciation. The investable universe is actually located in the specialized secondary supply chain, publicly traded companies that provide the components and materials required by the government operators. To enter this supply chain, companies must hold elite regulatory credentials, such as an ASME N stamp, a quality assurance certification from the American Society of Mechanical Engineers, or an NPCIL Class 1 qualification. As this funnel illustrates, thousands of contractors provide general parts, but only an elite fraction meet the standards for nuclear components. These regulatory moats take up to 7 years of relentless audits to obtain, making it impossible for competitors to quickly enter. Building wealth in this sector requires identifying the specific supply chain bottlenecks protected by these certifications and holding them through a 20-year structural expansion.